Okay, these are the notes from class on determining molecule polarity. This would be on pages 21 and 22 of your Unit 5 packet. So molecule polarity describes an imbalance of positive and negative charge around a molecule, which can then help us determine different properties of the molecule based on the types of intermolecular forces that would occur between them. So to understand those properties, the first thing we have to do is figure out the polarity of the molecule. So these are the general steps that you're going to follow. First step is you're going to draw the Lewis structure. So we know how to do that. We know how to figure out the shape using Vesper theory and make sure you have the correct angles. Then the hard part is figuring out the molecular polarity. So what you would do is draw your molecule with the correct shape to it, and then you'll want to kind of jot down the electronegativity of each atom in the molecule. So for example, we have water here. These numbers might be a little different than the ones on your purple sheet, but you're going to go to your purple sheet and look up those electronegativities. And really what we want to do is see if the surrounding atoms on the central atom are pulling with equal strength and in opposite directions. So here you have water with all the electronegativity values jotted down. We have carbon dioxide, which is a linear molecule. Those are all jotted down. And we have formaldehyde. So we've jotted down all those electronegativities. Then the next thing you're going to do is figure out the polarity of each covalent bond by doing the subtraction. So for example, the type of bond here between oxygen and hydrogen, we would take, based on the numbers above, 3.44 minus 2.2, you get a difference of 1.22, which is a polar covalent bond. Same thing between carbon and oxygen, we get polar covalent, and then here, I think carbon to hydrogen, based on your unit packet, would be polar covalent. These are a little bit under. But in any case, you're going to look to see which direction are the electrons being pulled. So the difference between hydrogen and oxygen, oxygen has a higher electronegativity, so the electrons would be pulled toward the oxygen and toward the oxygen, okay? With this carbon dioxide, oxygen's higher, so the electrons around these shared pairs of electrons are being pulled on harder by oxygen on both sides with equal and opposite strength. Okay. If we look at formaldehyde, so carbon has a higher electronegativity than hydrogen, so these get a slight pull toward carbon. And then oxygen is quite a bit higher than carbon, so we get a strong pull toward oxygen. Okay. So since, if we go down a little bit lower here, since carbon, so the CO2 molecule right here, since these have the same electronegativity values in opposite directions, these will cancel each other out. So CO2 is considered a non-polar molecule. There's no net polarities because the polarities cancel. If we look at the water, you'll see that the overall pull of the electrons is toward the oxygen side. So we draw what is known as a polarity vector toward the oxygen side, and then that is a partial negative and a partial positive charge. So these polarity vectors, you're going to go from the lower electronegative atoms toward the higher electronegative atoms. And then the partial positive, partial negative, the partial positive will be toward that lower electronegative side, and the partial negative is toward the higher. If we look and see how this adds up in formaldehyde, right here, the pull is toward the carbon and then toward the oxygen. So overall, that the pull is toward the oxygen side. So we've got a polarity vector here going toward oxygen with a partial negative at the arrow end and a partial positive at the positive end. Okay. So these polarity vectors, which I just showed you, now you can work it out by the bond and then do it overall, but really what I'm going to have you guys show is that molecule dipole. Okay? And then you're going to drop in the partial positive and partial negative charges on top of that. Okay? So here's a flow chart on the next page that can help you with figuring out these decisions. But we're going to go down here to the practice and see how this all works together, and then add in some London dispersion, or add in some intermolecular forces as well. Okay, so our first one is SiO2. We're going to draw the correct Lewis structure with the right angle. So SiO2, you have a silicon in the middle and oxygen on either side. We need a total of 16 electrons. I've used 2, 4, 6, 8, 10, 12, 14, 16. So this happens to be a linear shape. Okay, just because it's linear does not mean that it's going to be a nonpolar molecule. We want to look up the electronegativity values. Okay, so if I look up these values, silicon is a 1.8, and each oxygen is a 3.5. Okay, so the oxygens are pulling with equal strength and in opposite directions on these shared pairs of electrons. So they cancel each other out, which means overall this is a non-polar molecule. And if it's a non-polar molecule, that means the strongest type of intermolecular force between other SiO2s. I've had a whole bunch of SiO2s together, like as a pure substance. These would all have London dispersion forces between them. Okay, where London dispersion are nonpolar. Those are for nonpolar molecules, diatomic molecules, noble gas atoms. Dipole are for polar molecules. Hydrogen bonding are also polar, where hydrogen is bonded to N, O, or F. Okay. All right, so let's try OF2. This one we need to have 20 electrons. We'll put oxygen in the middle, attach each fluorine. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 2 bonds, 2 lone pairs makes this bent. So I'm going to redraw this. Oxygen here, each fluorine. So now I'm going to add in my lone pairs here and here. Okay. Now this one, I'm going to look up the electronegativity values. Oxygen is a 3.5, and each fluorine is a 4.0. Okay. So the pull of the electrons is actually toward the fluorine. Okay. So this is not equal and opposite. There's a polarity to this molecule. So overall, I'm going to draw in a polarity vector. I'm going to need a different color to do this. Let's go with this bright blue. Okay. Oh, there it is. Okay. So I'm going to draw in a polarity vector showing that the pull of the electrons is toward the fluorine side. So I have a partial negative here and a partial positive on this end. So this is a polar molecule overall. There's an imbalance in the pull of shared pairs of electrons. This is going, if I had other OF2s around, they would have dipole forces between them, because in this case, there's no hydrogen, but it is a polar molecule. All right, let's try CCl4. So for this one, it's going to be tetrahedral, carbon in the middle, chlorine, 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 and a full house here for a total of 32 electrons. Okay, so this is tetrahedral. Okay, if I look up the electronegativity values, I could see that carbon is a 2.5 and each chlorine is a 3.0. So the electrons are being pulled toward the chlorine, but it's equal and opposite. they're all being pulled with the same strength at 109.5 degrees. So all of those polarity vectors, they would cancel out, deeming this molecule as nonpolar, which means the strongest forces of attractions would be London dispersion forces if I had a whole group of CCl4s together. Now, what might happen if we were to switch out? Oh, goodness. If we were to switch out a couple of these atoms to being hydrogen atoms, okay? So if I want to put carbon in the middle again, I'm going to change these to hydrogen. And put those lone pairs on there. Okay, so we know that carbon is a 2.5, chlorine is a 3.0. Okay, hydrogen, if I look that up, is a 2.1, which means that the electrons are being pulled toward the carbon because carbon's a higher number, and then these share pairs are being pulled toward chlorine. So this is not equal and opposite. So overall, there is a molecular polarity. The electrons are being pulled toward the chlorine side, so I lay in my polarity vector there for the molecule with a partial positive and a partial negative. Okay, so this is again tetrahedral, but this molecule is a polar molecule. And yes, there's hydrogen, but it's hydrogen bonded to carbon. So this is still dipole-dipole since it's polar, but there's no hydrogen bonded to NO or F. Okay, let's try HCN. So we need a total of 10 electrons. Carbon will go in the middle, attach nitrogen, attach hydrogen. So 2, 4, I'm going to do 6, 8, 10. We've drawn this one a few times. This is linear. Now, just because it's linear does not make it nonpolar. Let's look at the electronegativities. So carbon is a 2.5. Hydrogen is a 2.1. Now, nitrogen over here is actually a 3.0. So electrons are being pulled toward the carbon, and then these share pairs are being pulled toward the nitrogen. So overall, the molecular polarity is toward the nitrogen. So that side is going to be partially negative. This side is partially positive. Okay? So this is a polar molecule. And again, dipole-dipole, yes, it has hydrogen, but the hydrogen is bonded to carbon. Okay? For it to be hydrogen bonding, hydrogen has to be bonded to NO or F. Okay? So the practice is on the next page. Your foldable will help you with the top. Few questions, and then at the bottom, there's some practice with drawing. Get this to move down. You're going to draw the Lewis structure. You'll draw the Lewis structure, and then if it is polar, then you'll use your polarity symbols. So if it's polar, you're going to show the dipole arrow and the partial positive, partial negative if it's polar. And then based on the polarity, nonpolar is London dispersion forces would be the strongest, dipole-dipole for polar, and then hydrogen bonding if hydrogen is bonded to NO or F. So you'll record that here. So choices here are LDF for London dispersion, dipole-dipole, which we can abbreviate DD, and then HB for hydrogen bonding.